So yeah, to kick it off this morning, we're going to talk about reasoning, and we've got three really interesting talks. And pretty much any AI system needs to have some kind of logic to do its reasoning, but logic on its own is sort of lacking in some ways, and so this morning we've got merges of logic with probability, with simulation, and with iconic representations. And it should be interesting, and hopefully we'll get lots of good discussion going. The first talk will be Matthew Ikle on probabilistic quantifier logic for general intelligence, indefinite probabilities approach.
I'm going to be talking today about our recent work with quantifiers in a probabilistic reasoning system that we've developed. The system we've been working on, myself and Ben, for quite some time is called Probabilistic Logic Networks. It's a probabilistic logic inference system. The idea is we want to unify probability and logic in an uncertain reasoning system. We've developed it as part of the Novamente AI system, but it's meant to be independent of Novamente so that it could be integrated into other systems as well. So some of the underlying principles that we wanted to incorporate into the system is the full scope of inference required, including intentional, extensional reasoning, first and higher order logic. Some other things that we need to make sure is that everything is computationally tractable and able to make use of inputs from non-logical mechanisms. So one of the issues that comes up that's critical here is not just what the probability is, but how much confidence, how much evidence there is for an individual strength value or probability value. This is important in areas such as belief revision. Multiple ways to get there, including our own approach, which will be an interval-based approach right there. Pei Wang's NARS system, also to whom we owe a lot of debt as kind of a motivator behind the probabilistic logic networks. Peter Wally developed a system based on envelopes of beta distributions, which he called imprecise probabilities. We'll look at that a little bit. And then some more heuristic approaches to getting at weight of evidence. Some key points about within probabilistic logic networks, PLN, we have multiple truth value types. The main truth value type that we use is what we call indefinite probabilities. I talked a little bit, I don't want to go into too much detail here about Peter Wally's imprecise probabilities, which for actual reasoning tends to give results that tend to say, well, in the end, everything is true with some probability between 0 and 1. Well, true, and we can say that probably with confidence close to 1. True, but not very useful. So we developed indefinite probability as a hybrid between Wally's imprecise probabilities and using ideas of Bayesian credible intervals. And this tightens those bounds up quite considerably. Now, in the past, we've given some talks about some of the inference rules that we've developed for PLN. And today, what I want to talk about is using PLN with quantifiers such as for all, there exists, and so forth. I said I'd try to keep this short. I'm not going to talk too much about this slide. These are more of the underlying details. I guess the one thing I would like to say is that in the indefinite probabilities approach, we use a 4-component truth value. And the idea behind this is trying to get an approximation of an entire distribution. The details are in the paper and in previous papers, and so I won't try to go there right now. So some of the goals we had in mind as we were developing quantifiers via the indefinite probabilities is we wanted logical and conceptual consistency. In the limit case, agreement with standard quantifier logic for the crisp case. There's some subtleties involved here, and that's the parentheses there, for all expressions to which standard quantifier logic assigns truth values. We're going to have truth values on certain objects that won't exist in standard crisp case. We want intuitively reasonable results, compatibility with probability in general and with the PLN system in particular. The key component here, we want to be able to extend quantifiers to include both crisp quantifiers as well as fuzzy quantifiers. So in order to do this, again, this gets into some of the details. Indefinite probabilities in general considers envelopes of probability distributions. And in order to incorporate quantifiers, we essentially introduced a third order probability that one could view as errors in measurement or perturbations of a higher level probability of the indefinite probabilities approach. So how to put that into context?
Can you set that to music?
Could I set that to music?
Yeah.
Probably in a certain sense, but I mentioned some subtle details here about the reducing to the crisp case where it assigns, in those cases where the crisp case assigns a value. This introduced a slightly non-standard semantic approach. Again, I'm not going to go through all of these issues right here. If you want to read them, they're up there. So I would like to talk a little bit about how it actually works. So here's the case for the for all quantifier. So we suppose we have a probability, an indefinite probability for a particular expression, f of t. It's got an unbound variable t. And what this does is it's trying to summarize the idea of an envelope of probability distributions corresponding to that expression. And from this, we want to derive an indefinite probability for the case for all x, f of x. So in order to do this, we'll consider an envelope E to be part of a higher level envelope, which is an envelope of envelopes. Given that we've observed E, what is the chance that the true envelope is in some interval, is almost entirely, supported within some envelope, or within the interval 1 minus E. E is some small, for all, it would be fairly small parameter. The latter interval 1 minus E to E is considered to constitute the concept of essentially 1, or with probability almost 1. For the there exists case, it's a similar concept. Here, the idea is we're going to have, in place of the interval 1 minus E to 1, we're going to consider an interval near 0, so 0 to E. So the world is not entirely supported within 0 to E. So we need to define what we mean by almost entirely. So in the for all case, we mean that the fraction contained is at least some value, which we call the proxy confidence level. And in that case, then the interval, proxy confidence interval to 1, level to 1, represents a fraction of bottom level distribution, so the lowest of the 3 levels, completely contained in 1 minus E to 1. In so doing, with this formalism, we realized that this lent a fairly natural extension to fuzzy quantifiers, in the sense that we have this interval proxy confidence level to 1 representing for all. Well, if we just replace that interval, proxy confidence level to 1, with some other arbitrary interval, which you could define, we could come up with ideas for fuzzy concepts, for fuzzy quantifiers. So for example, the interval 0.9 to 0.99 could be an interval that would correspond to almost all. Something like 0.5 to 0, or 0.05 to 0.1 could constitute, and you can define these how you want, as being something representing a few, or not very many, or whatever you wanted to call it. So to summarize the basic ideas, we normally have 2 levels of distributions in the indefinite probabilities approach. We introduce the 3rd level as perturbations or errors of measurement. And this allows for a sort of sliding scale of fuzzy as well as crisp quantifiers. And it is actually computationally tractable. So what was the time on that?
You're really close.